This question is asking, use small error analysis of PLL to show that a first order loop h of s is equal to 1 cannot track an incoming signal whose instantaneous frequency varies linearly with the time theta I of t is equal to kt square. This signal can be tracked with the constant phase. So if h of s is equal to s plus a over s, it can be tracked with zero phase error if h of s is equal to s square plus as plus b over s square. Here we have three situations. First, we had to prove that it cannot be tracked. This first order, like use small error analysis of PLL to show that first order loop cannot be tracked incoming signal whose instantaneous frequency varies linearly with the time. So here we had to just prove, like, if it varies with linearly with the time, we cannot track the incoming signal. Okay. And also we had to prove that this can be tracked with the constant phase error, and we had to prove this one can be tracked with zero phase error. Now let's see how to do that. First, let's write the given information. Here we have theta of I. Theta I is given by theta I of t. This is in time domain, and that is equal to kt square. And in order to analyze the error, we use this formula, that is theta E of s, that is equal to s over s plus ak h of s, and theta I in the Laplace domain. So here this is in time domain, so in order to apply that one in this equation, we have to find out the Laplace transform of this. So if you find the Laplace transform of this, that is theta I of s is equal to 2k over s cube. This is the Laplace transform of this. Now we can plug that one in this equation and figure out what we get here. So if we plug that one, that is s over s plus ak h of s h of s, and that is that one also. Okay, that is only this value, and also we had to substitute the theta I of s value, that is 2k over s cube. So we multiply this one by 2k over s cube, and if you do that, this s, one of the s will be cancelled with the top, so we will get s square here. So and the 2k will be on the top, so we are going to have 2k over s square in the denominator, multiply that one, this one multiply with this, so s plus ak h of s. Okay. So no, to see whether the signal can be tracked, we had to use the theorem called final value theorem. In the final value theorem, if we apply the final value theorem, we will know the final answer, like whether it's 0, infinity, or some constant value. We are going to know that by applying the final value theorem. So here, first condition is they mentioned that h of s is equal to 1. So we have to see at that condition what's going to happen here. If h of s is equal to 1, and using the final value theorem, we have the final value theorem is basically you take limit t approaches infinity in the time domain, theta E of t, and that is in the frequency, that is in the Laplace domain, that is limit s approaches 0 and s theta e of s. Okay, that is in the Laplace domain. Now we can go ahead and substitute the values we have derived in the Laplace domain and see what we can do with that. Okay, so if I apply that, limit s approaches 0 and s times theta e of s, that's the one we figure out right here. This is theta e of s right here. And if I substitute that value for here, that is 2k over s square times s plus ak, and here we are looking for h of s is equal to 1, so I just substitute the 1 for it. So when we substitute 1, it's going to be same, like it's going to be ak, and I just leave it like this. And here also this s and s square can be cancelled, so this can be just written as s here in the denominator. Okay, so now we have this one, s times this, and if I substitute 0 for this, you see in the top we have 2k, and in the denominator we have 0 multiplied by this and this, so the denominator is going to be completely 0. So if you divide a constant value by 0, that's going to be infinity, so we get infinity. So therefore we can say the incoming signal cannot be tracked here. Hence the incoming signal cannot be tracked. Okay, so this is when h of s is equal to 1, and they have given another two h of s values. We have to see, and they also mentioned this can be tracked with a constant phase, and they have given another one, and that can be tracked with a 0 phase error. Okay, so we have to make sure like we are gonna do these things next, and let's do this one next. H of s is equal to s plus a over s, and we have to prove this one can be tracked with the constant phase. Now to prove that, again you have to just use the final value theorem. We have derived up to this point, right? So the only difference is h of s value, we apply 1 for it. Now we have to apply s plus a over s for it. So we can just mention that if h of s is equal to s plus a over s, and using the final value theorem, we know that limit e approaches theta is theta e of t in this time domain. In the Laplace domain, that is limit s approaches 0, s theta e of s, and limit s approaches 0, and then s remains the same, and then instead of theta e of s, we put this one. Okay, that's 2k over s square times all this, and the simplified form is also here. We already simplify like this. In this case, we just have to substitute the, here we substitute 1, that's why we have just a k. But if we substitute s plus a over s, let's see what happens. So this is 2k over s times s plus ak, and here we are substituting s plus a over s for the h of s value, so let's substitute right here. Okay, now this one multiply both of them, this and this, So when we multiply this one by this, approaches 0, this is 2k, and then here we're going to have a s square, and if you multiply this one by this s and s cancels, so we are going to have ak times s plus a. Now if we substitute 0 for it, this term will be 2k will remains, and then this term will be 0. ak times s will be 0 because s is 0, and then ak times a gonna remain, so this is going to be aka in the denominator. Okay, so finally we managed to derive a constant value, so we can say that this incoming signal can be tracked with a constant phase 2k over aka radians. Hence the incoming signal can be tracked within a constant phase (2k over aka radians). Okay, so this is when h of s is equal to s plus a over s. Now we have another condition, that is it can be tracked with 0 phase error if h of s is equal to a square plus as plus b over a square. Let's go ahead and try to prove that. Again, same method, exact same thing, and the only difference is h of s is going to be changed, and we have to apply the final value theorem again as well to determine if it's giving 0 in this case, because they mentioned that it can be tracked with 0 phase error. So let's do that. So if h of s is equal to a square plus as plus b over a square, and using the final value theorem, we have the final value theorem is limit t approaches infinity when theta e of t, and that is in the Laplace domain. S limit s approaches 0, and we already simplify this one. That one should be s times theta e of s. We can also mention that s theta e of s, and we have the simplified form, that is this, and here in this one is after applied one, but here we had to apply the new one. So let's go ahead and apply that. So this is limit s approaches 0, and then 2k over s plus 2k over s times s plus ak, 2k over s times s plus ak, and instead of h of s we are going to apply this one, that is s square plus as plus b over s square. Okay, now we can multiply this s with everything, so this is going to turn into limit s approaches 0, 2k over s times s square, and then when we multiply with the second one of the s will be cancelled because this s and this s square, so we are going to end up with having ak times s square plus as plus B over S here. Okay, so this is what we are having here. Let me double check SQR here, and then AK times S, and this S will be cancelled with this. So we are going to have a S in the denominator. Okay, let me double check this one. So here we have 2k S times S plus AK times H of S, 2k S times S plus AK times this, and S times this is S square, and S times the whole thing, S will be cancelled. One of this will be cancelled because we have S square in the denominator. Okay, so we end up with S. Now let's try to simplify this one furthermore. So to get rid of this S in the denominator here, because currently if I apply 0, I'm gonna have like 0 by 0 situations. I want to avoid that, so I multiply the top and bottom by S. If you do that, then I can get rid of this denominator S here. So this is going to be S approaches 0. We're going to have 2k S here, and then all the things denominator also multiply by S. So this is going to be S cubed right here. And when I multiply this one by S, this S in the denominator will be cancelled. So we are going to have AK S square plus AS plus B. Okay, now if I substitute 0, this is going to be 0, this is going to be 0, and then AK square, that term will be 0, and then this AK times AS, that also 0 because we have S, and only terms that will be remaining is AKB, so 0 over AKB. You divide a 0 by a constant, that's also 0, so the final answer is 0. That's what we had to prove, because it's mentioned here it can be tracked with 0 phase error, and we have proved that one right here. Finally, we can write a statement saying hence the incoming signal can be tracked with 0 phase error. Okay, that's it for this video. I hope you guys found this video helpful. Thanks for watching. Don't forget to subscribe my channel. See you guys on my next video.